Hello and welcome to another tutorial. We are going to continue our discussion on passing values or arguments when we call a method, and we already talked about pass by value, the concept of pass by value for primitive data types. If the type of a variable that you pass a method or the type of parameter is an integer, basically a primitive like an integer, what happens? And now we are going to look at also the reference types, because we said that in Java variables, the type of variables falls into two separate categories. One is the primitive types, and Java has this nice capability that it supports primitive types like the native primitives that the CPU understands, and it also supports reference types. And we said that references in Java are just syntactic sugar for pointers in C++, but Java decided to drop the pointer notation like those asterisks that we use, because it just makes the code source code look ugly. So Java dropped that, and then we have basically reference notation, which means when we create a new object, we have a reference to it. All the pointers or references are stored on the stack of each method, right? Remember, when you launch your application, you are essentially in the stack frame of the main method, right? That's the entry point to your Java application. And then in your method, in your main method, you might call other methods. So you go into the stack frame of the other methods, and then at any point during your application, you might create some sort of object. So whenever you create object in Java, you always use the new operator, and those objects are always stored. The state of the object is stored on the Java heap, and you always get a reference to that memory location in your source code, basically, which is always stored on the stack, right? So references are stored on the stack. That's not true for the variables that you define. So local variables are also stored on the stack. Parameters of the method are also stored on the stack, basically a stack frame of the method. But then objects are created on the Java heap, and then the state of the object is also on the Java heap, right? So there is a difference between what sorts of variables are basically stored on the stack. And again, basically local variables, the parameters of a method, and then the references to the objects that you create inside the body of your method, those are the ones that are created are stored on the stack frame of the method, right? But then references are special because they are pointers, right? They are just glorified pointers, and they're pointing to a memory location on the Java heap that stores the state or the data associated with a particular object that these pointers pointing to, right? So references are like local variables. They're stored on the stack of the method, but then the actual state of the object, the state means the data that the object holds, they are stored on Java heap. That's just because Java heap is much larger memory area than the stack frame of each method, right? You cannot have infinite amount of memory for a stack, and that's why we have the stack overflow error. Now in Java, because it's a virtual machine, obviously there is a flag that you can change how much memory is going to be allocated to the stack frame of each method. And that's the nice thing about running your application through a virtual machine, because then there are some flags that you can tweak. But then, for example, when you in other programming languages like C++, the ones that directly compile to the machine code, the amount of memory that allocated to the stack of your application is always, or basically the main method of your application is always determined by the operating system, right? But for Java, which is a virtual machine, you can tweak that memory. But usually people don't touch that, so usually you always use the default amount of memory that the max or the default maximum amount of memory that the JVM allocates to the stack frame of each method, right? So I'm going to create a new class. Let's say pass by value references, or let's just call it pass by reference, which means we're going to have a method, but that method is going to, the type of parameter is going to be a reference to an object, right? An object type. And again, a reference type could be any of the types that we defined in Java, like an interface, a class, an enum, or basically a record, for example. That's a new addition to Java. So the concept here is that reference data type parameters such as objects are also passed into methods by value. Again, everything is passed by value, right? That's how the Java JVM operates, passed by value. And we said that for primitives, it literally means that when you write a method like this and have a primitive variable, it will, the way the JVM sees this line of code when you run your application is equivalent to copy whatever value that X holds, and then you actually, JVM sees this interpretation that the variable is replaced by the actual value. And then what this means is that you can never change this variable, which is a primitive type, when you go into the method call, into the body of the method, because this variable has nothing to do with the method, because what the method sees at runtime is the value of the variable. Now, same with references. The difference is that references, now you cannot change the value that the reference is holding, which is a memory address, but then because you have the memory address, you can always follow that memory address and access the object, the state of the object on the Java heap. And if you're allowed to modify the state, mutate the object, because access modifiers might allow you to do that, then you can mutate the object itself, the object that that reference is pointing to. So let's go through this and then I'll show you a couple of examples to make it really clear. This means that when the method returns, the passed in reference still references the same object as before. Again, no matter what type of variable you pass, you can never change the value that the variable holds when you pass it as an argument when you call a method. You can never change that, which means I have a variable in my main method. I pass it as an argument when I call this method. When I return from this method call, basically when I'm at line 22, the value of this X is always the same value that this variable had before going into the method, before calling the method. So this is true for any job programming that basically implements the pass by value. Okay, so I want to be again very clear about this. Variables can be primitive or reference types, and when you call a method, obviously the most use of variables is you want to have meaningful names, and then use those names which is easily to write and remember, and then use them as arguments when you call a method. But a method in Java can never change the values that the variable holds when you return from the method, right? So just be very careful about this. However, the values of the objects fields can be changed in the method if they have the proper access level. And again, what this means, if you pass a reference type, you have a memory address, right? So basically this variable, for example, in this example is a circle type, which means, so we have some primitives and the values that these hold directly gets copied. This circle is a reference type. And again, what this means is a pointer, it's a memory address. And when you call this method with a reference type variable of type circle, that memory address is copied into the local parameter or local variable, right? The parameter is a local variable to the method. But then regardless of what kind of, if you have multiple variables that have the same memory address, you can always use any of them to basically access the object in the Java heap, right? The same object, because regardless of if you have multiple variables that are pointing to the same object, you can use any of them. So if you copy one reference variable into another, both of them are pointing to the same object. Now let me explain what it means. So you can copy, so first of all, let's see case one for primitives, right? And again, this is not just about calling method. This is a general idea of copying variables. Let's see what happens. Now case one, primitive. So I create x equals 5, int y equals x. Now what we're actually doing, here is copying a variable, right? And what the Java compiler does, first of all, assignment operator, the left hand side is evaluated first, which in this case the JVM just, when you run your application, the JVM just loads the value of x, right? That's how you evaluate just an expression like x. And then for the assignment operator, then the result of evaluating the right hand side is going to be applied to the left hand side, as long as the types are compatible, which means that if the compiler can do an implicit conversion, for example, is if y is long, this is a still valid, we can do a implicit conversion from int to long. But if this is short, then obviously the types don't match and you cannot implicitly convert into short, right? Well, let's say these two have the same type. So the point that I'm trying to make here is about copying. How does the copying work in Java, right? So case one, primitives. If you do this, so let's do a sysout x equals and then plus x, and then sysout y equals plus y. And obviously if we run this, x and y have the same values. But note that we copied x into y, and this for primitive, it means literally allocate a new memory on the stack frame of this method, and then push the value that x holds into that new memory address, into y, right? That's the meaning of primitive variables. But then if after doing this copy and this new variable is created, if I say x equals 10, I'm changing the value of x. The question is, does the value of y change or not? And the answer is no. So this has no effect on the value of y, because assignment in Java is basically copy by value, right? That's the meaning of copy by value. We are literally copying the value of x into y, and x and y are two separate memory locations in the stack frame, and changing after creating y and initializing basically with the value of x, or copying the value of x into y, changing x further doesn't affect the change of y. Now in programming languages like C++, you can create references or memory address. You basically create a variable that holds the memory location of that primitive types, and then changing to any of them, x or y, changes the other one. So in Java you don't have that kind of capability, so it's always copying by value. So originally we copy x into y and both of them hold the same value, but then changing the x again doesn't change the y. So if I run this, I'm going to get x10, but y is still 5. And the same story, if I change y, then x doesn't change. So x is still 5 and y is 10, right? So these two have no effect because we literally copied by value. And again, when you pass a variable to a parameter, the copy by value happens, right? So parameter has its own memory location on the stack frame of the method. You just copy the value of your variable when you call that method into the parameter or the local variable of the method. And after that, that parameter, which is a local parameter of the method, has nothing to do with the variable that you pass to the method when you call it, right? Now note what happens in case 2 when we're dealing with reference types, or basically glorified pointers, or handicapped pointers, right? So references in Java are handicapped pointers. What this means, they kind of are like pseudo pointers, if you wish. These are like pseudo pointers. Basically they're pointing to an object behind the scenes, but all those are basically hidden from the developer. So you don't have the same capabilities that you have as if you were using pointers for Java in C++, for example. And that's for a good reason. That's just memory safety, right? Memory safety, which means the developer doesn't directly touch the memory. JVM manages that, and that's just because JVM has a very complex internal, which also includes the garbage collection, memory management, etc. Now let's say I have a type here. Let's create a type outside this. Let's call it circle, right? And then this circle is going to have int x and y, and we have a public constructor. Actually, it doesn't matter if this constructor is public, because this class cannot be public. In every source code we only have one constructor class that is public. And then regardless of whether this class is public or not, because the access for the type itself is restricted to the package level access, it doesn't matter if you have a public constructor or not, because other classes in other package can never invoke this public constructor. That's just because they don't have access to the type. And again, this was a very important concept that we discussed when we discussed the idea of packages, that accessing the type is separate from accessing the constructor of a type. So if the type itself, the access to the type is restricted to the package level access, there is no way that another class in another package can call this public constructor, even if it's public. So if you have a package level access for your type, it doesn't matter if your constructor is public or package level access, because those basic, in this case, they mean the same thing, right? Because if somebody doesn't have access to the type, they definitely don't have access to the constructor as well, right? All right, so let's see what happens. And these X and Y are also package level access, but that's fine because we're in the same source code, so we're going to directly access these values. So let's say circle C1 is, we use the new operator to call the constructor, and because I provided an explicit constructor, then there is no basically no R constructor anymore. So let's use the autocomplete feature and say that we want to have this constructor in X 2 and 3. And let's also quickly override the basically toString method to just print the values of X and Y. Basically, usually toString is a nice feature to quickly override and print the state of the object, or the part of a state that matters the most to us when we are developing our library and we want to do some debugging. So toString is, I personally usually use it when I want to like look at the state and debug something. So if I create this C1 and say sysout C1, it's just going to call the toString method on it. So circle X2 and Y3. Now note that what happens if I say circle C2, I'm defining a variable. At the moment, I'm not creating a new object. I'm just saying that there is a variable C2 of this type. And again, every variable in Java has to have a type. And then we can either create a new object or copy the value of C1 into C2. So again, this is copying some variable, right? Copying a variable C1 into C2. And the copying is basically happens by value again, happens by value. What this means, we literally copy whatever value is in the memory address on the stack frame. Remember, this is a local variable, so there is some memory on the stack frame, and the value of this variable, there is some value at that memory address, that is the value of this variable, and we literally copy that into C2. Now if I change C1, and the difference between primitive types and this reference type, this case is that now C1 and C2 both point to the same object on the Java heap, on the Java heap. And this is very easy to understand, right? C1 had the value that is stored in C1 is a memory location on the Java heap that has the this object, right? This object, the state of this object, because it's just an X and Y, is stored somewhere in the Java heap, right? And then this pointer is pointing to that state, that part of the Java heap that holds the value of X and Y. Whenever you have an object, basically it has some state, and that state is going to be stored somewhere in the Java heap in the memory, right? That's the whole meaning of creating objects. And now we're saying that C1 and C2 basically point to the same object. What this means is that if I say C2.x minus 10, so I use the value that C2 holds, and which is again the memory address of the object that C1 is also pointing to. And if I do a sysout on C1, I expect that now the state of the object has changed. Yes, minus 10. Basically what this means is that when you're dealing with objects or pointers, it doesn't matter how many variables point to the same object. You can use any of them to mutate the state of the object itself. So basically both C1 and C2 can be used to access the state of the object on the Java heap. Again, this is a subtle difference between primitive variables and reference variables. And again, reference variables are syntactic shortcuts for pointers. And the difference between primitives is that when you create a primitive, regardless of whether you directly write some value to initialize it or copy another variable into the new variable, these variables are completely independent, right? Same here, C1 and C2 are two separate variables. They completely independent. But when it comes to getting to the state of that object, because both of them are pointing to the same object, you can use any of them to mutate the state of the object. Now let's look at this one. Now let's apply this to pass by value two methods, right, for method calls. Public static, I'm going to declare this method static because the main is static. So you in a static method you can only call a static methods. Public static void basically method call with reference, right? And we're going to pass a circle C, and then we're going to say change the X, right? So we want to pass an X variable, which is a primitive, and then circle C, and inside we're going to see that C.X is X. Okay, and this line works again. These variables in the circuit in the state have package level access. We are in the same source code, so no problem, we can access them. And then now let's see what happens if I so now case basically pass by value for reference types. Now if I say basically method called reference, if I pass C1 and then pass let's say 25, right? Now what happens here is that this C1 when we call this method pass by value means this will get translated into the actual address, some address, right? Now if we want to kind of get the idea of what the address means, we can say C1 dot basically so the default implementation, if we don't override the toString, we can see actually what the kind of hash code or memory location is. But for now, what happens here is that whatever memory location, let's say it's hex 0xFF2576, right? So at runtime, when you run your application, when the JVM hits this line, what it does is just reads what's the value of C1, and C1 is a reference type, which means it's a pointer type. The value that C1 holds is a memory location that points to the object. So at runtime, pass by value means this line gets translated by copying the actual value the variable holds into the method arguments, right? Actually, so the JVM sees this. Right? This C1 has no meaning at runtime. JVM sees this, that, oh, okay, so this method is called, the first argument is some sort of memory address, and the other one is some integer, right? Again, JVM doesn't care the variables or what's going on, because Java is passed by value. Before the method call, all the values of the variables are copied into the parameters, and then the stack frame for the parameter for the method is created. These values that you actually passed are copied into the parameters. So here when we call this method, C becomes a local variable and has this value, for example, right? And then X is an integer and has 25. Now when we do this, basically what we're doing, we are dereferencing this memory address. And again, now both C and C1, they're pointing to the same object because they hold the same memory location information. So in this case, C is independent of C1, right? C doesn't know about C1 and it doesn't care. C1 has nothing to do with this method call. Again, C1 has nothing to do with this method call because at runtime, just the only thing that the C1 does is JVM copies the value of C1 into the first argument, and then JVM works with this representation. So JVM doesn't care about C1 when you go into the method, right? So C is independent of C1. This variable C, this local variable or the parameter, doesn't have any information about C1, but it holds a value, but it holds the same memory location or the same pointer information as C1 or C2. All right, which means when we say c.x, which means we are accessing the state of the same object that C1 was holding and the C2 was pointing to, right? So if I come back and let's say cout C2, C2 is still pointing to the same object that C1 was pointing to, and now C is also pointing to the same object. So if we mutate the state of the object based on C variable, it will be reflected into C2 when we access the state through C2. So when we come back from here, x is 25, right? So variables of type reference or pointer type are independent of each other, but because we copy the values that these pointers hold, these references hold, and the values are the same memory location pointing to the same object, then mutating the state of the object through one is reflected into reading the state from other objects, right? So so in Java, copy happens by value, but then for reference types, we can mutate. We can access the same object. Basically we can access the same object via multiple reference types, right? Could be a variable, could be a local variable of a particular method. This variable only exists on the stack frame of this method. C1, C2, they're local variables. They only exist in the stack frame of the main method, but they are all pointing to the same object. So I can access this object that I created and via any of them, and I can mutate the state of that object via any of them, right? Now notice what happens if when I pass some variable to it, which means I copy the value of C1, and when this method is called, the C is initialized with this variable. But we've seen that we can assign new values to a local variable, right? A parameter. That's completely allowed. That's legal. For example, in this method, I can, after using this x, I can say x is 100. That's fine. That's totally fine. But when I come back from this method call, this x, which is a local variable, is destroyed. So it has no effect after I call back from this method call, right? At line 45, there is no history of x. That's completely gone. So it doesn't matter if I change this local variable. And again, usually you pass param values or arguments to a method to do something with them, but in most cases you don't actually mutate those local variables, right? Those are placeholders. That's why one of the best practices is to declare them explicitly as final. Then if somebody reads this code, first of all, it tells them, hey, you're just the value of these parameters are going to be used, but we're not going to change them, right? Now in this, obviously, then if I have explicitly declaration of the final parameters, which means once you initialize them with the values that you pass, when you call the method, you cannot change the values in the actual body. As soon as these variables are initialized with the original values, you cannot change them. Basically, final variables cannot be reassigned, right? But then let's remove this final. Now there is no limitation that this C originally points to the same object that we created here, right? But there is no limitation that we can actually in fact reassign it. So we can say new circle -10 -20. This is completely legal. And obviously one question that people always ask in interviews, that if this is the case, remember, so let's comment this out. This C, we copy the value of C1 into C, but then when we call the new operator, new always creates a new object and returns the new memory location, right? Returns the memory address of the newly created object. And obviously this object is in a different memory location than the original one that C1 or C2 were pointing at, which means now C holds a value, a memory address that is different from this C1 and C2. Now people always ask, what happens when we come back from this method? Does it mean that we change the C1 or not? So let's see. So let's actually create the bring back this line. So we pass C1 and 25. C1, the memory location is copied. So originally C is pointing to the same object that C1 is pointing to. And then we use that C variable to mutate the state of that object. X is 25. But then C is reinitialized, reassigned a new memory address. What happens to C1 or C2, right? So let's see. So what do we expect? We expect that when we come back, again, in a method call, you can never ever change or mutate a variable that you pass as an argument, which means when we come back, C1 is still pointing to the same object that it was pointing to before going into the method call, right? I want you to understand it very clearly. We changed C, but C has nothing to do with C1. So this is still pointing to this object, to this memory location, all right? And this was, let's say this memory location was when we created this object. So this object is allocated at this memory location, and then C1 is pointing to, C2 is pointing to. We muted the state of this object via C2, so or X is minus 10, which C1, we can access C1 or C2 to access the state of this object. We pass C1 to this method, so the memory location is copied into C. And then we use C to access this memory location or change the state of the object at this memory location. So X becomes 25. But then now C1 is still pointing to the same memory location, but C is reassigned. And we don't care. We don't care if basically this. We can in fact write C.X equals X again. But then this is not going to, or maybe 2X. So the original object that C is pointing to gets a value of 25 for X. This new object, which is a local variable, right? Local object, or basically the scope of this object is limited to the scope of the method, gets a value for X, which is 2 times 25, which is 50, but it has nothing to do with the memory location that the C1 was originally pointing to. So basically, when we execute this line of code, what we expect to see is X is now 25, because the first line deals with the same memory location, the object at the same memory location. And then Y was whatever it was originally for the state of the object at this memory location, which is 3, right? So 25 and 3. So this, after reinitializing this local parameter, it has nothing to do with C1. So when we come back, C1 holds the memory location or points to the object that it was pointing before going into the method call. So this is the whole idea of pass by value. Now this is not the same as in C++. When you pass around pointers, you have to be careful. But in Java, you don't really need to have to be really careful, because you already know that if I pass a variable to a method call, when I come back from a method, that variable, whatever value it was holding, even if it was a memory address, which means it's pointing to some object, it's still going to hold the same value, right? A method call can never change the value that the variable is holding when we pass it to as an argument to that method. Because at runtime, what happens is that JVM doesn't see that C1 is passed to the method. JVM sees the method and the actual values. And JVM says, oh, okay, you're calling this method with this value for the first parameter, the second value, and then let's say here 25 for the second variable, right? JVM doesn't care whether this is called C1, C2. It only cares that what's the value of the first parameter. So I hope you enjoyed this lecture and now have a very solid understanding what is the meaning of pass by value when we call methods. You have to, again, be a little bit cautious about passing references to methods, because that references deal with a state of the objects. So if you pass a reference to a method, you can use that reference to mutate the same object, right? So mutating the state of the objects is, you have to be careful about it when you pass them to the method. So please stay tuned, and I'll see you in the next one.